Okay, now, so we are coming now to the second part of this demonstration, and I would like to tell you a little bit more about Matlab and polynomials. So I find polynomials, and most of the time I prefer to talk about a concrete vector space of cubic polynomials because they are so nice. You can easily imagine how they look like. They're clearly a four-dimensional space, therefore also the dual space will be four-dimensional. But on the other hand, they're concrete functions. And it's a translation invariant space. That's nice for illustration of topics in harmonic analysis. And the other thing is, of course, polynomials can be multiplied. So it's plausible and natural that you can work with polynomials in Matlab. And so, of course, in Matlab, they are not so much functions, and even plotting a polynomial might be an interesting thing. So let's first explain the Polyval command. And this one-line command is my standard starting point because it tells you very quickly, if you take a polynomial with the coefficient sequence 1 to 3, clearly this is now a quadratic polynomial because we have 3 coefficients, then you are getting, if you evaluate this at the point 10, you're getting this exactly the same number. It's also clear that if you take a few leading zeros, this would not change the result, of course. Whereas everybody knows, if you would put the zeros to the end, maybe we just do it. Polyval of, yeah, maybe like this. At 10, of course, you're multiplying with 1000. And okay, so there is a bracket missing, of course. And therefore, you're getting the number as we are used in our decimal system. Now, if you would like to work with another system, like a binary system or so, you could also use these numbers and compute with these things. Now, a funny game for illustration relating the multiplication of integers to the multiplication of polynomials is this one. Everybody knows 11 squared. Maybe you don't know directly from your heart, so what the third, the fourth power is. And it looks very nice up to the third line and say, oh, this looks like the binomial coefficients. A plus b to the third power is a third power plus 3 times a squared b plus 3 times a b squared plus 1 times b third power. But here it starts to get not as you like it, because it's a little bit asymmetric or so. And then I'm telling you, well, if you would multiply polynomials, you would, I don't know, have something like 3 times 5 is 15. Write down 5 and move the 1 over to the next place. So this is, of course, happening when you multiply numbers. Whereas if you multiply polynomials, you're keeping the coefficients. Okay, so what is the way to multiply polynomials? So in school, you would say, I'm just multiplying out, having all kinds of products of different powers of x, and then I'm sorting it. So if I'm smart, I'm arranging all the entries that are coming by the multiplication. All the x squared, x third power are put together in a natural way. And then I'm saying, well, how much of this power do I get? And now this is, of course, known as what we say the Cauchy product. You're adding up all the products of coefficients which add up to the same power. And this is exactly the convolution. So convolution will be introduced in this course in several different ways. But the polynomial multiplication is maybe the most close to elementary school. So I call BI for binomial coefficient, and I do convolution. So I'm saying, what happens if now I should read this in standard terminology, the polynomial with the coefficient sequence 1, 1. And as you have seen from this example here, it starts with the leading coefficients. So if you see two coefficients, then you would say it must be a linear function. It has two coefficients. It's enough to know a linear function at two places. It's describing a polynomial of degree 1 or order 2. So the length of the vector is the formal order. It's the number of coefficients, but obviously we start polynomials with a monomial basis. We start to use it in the mathematical terminology with 1x, x squared, and so on, up to x to the n minus 1, or we want to go up to degree n, then we need n plus 1 coefficients. Now, what you've seen is that Matlab is using the convention that is used in the representation of the decimal, so it starts with the leading coefficients. And this is sometimes one has to take this into account. However, the corresponding choice of basis, which is Matlab chooses for the Polyval command highest power first, and mathematicians use lowest power, means 0 power first, constant 1 as a first term. Doesn't matter when it comes to convolution, because it's very easy to show. When you know convolution, you would say the flip operator is compatible with convolution. If you flip two functions and you convolve them, you're getting the flipped version of the convolution product. Here you would say, if I change the basis from the ordinary monomial basis to the flipped version, and you do convolution, you get also the flipped version. So in this sense, it's harmless. And here we have even a symmetric situation, so it's absolutely clear that you will get x plus 1 squared. X plus 1 multiplied with x plus 1 is 1, x squared plus 2x plus 1. Now, if you do this in a repetitive way, and here you see in a simple example how to do for loop in Matlab, with maybe the small side remark that if you're asking me what the outcome is and why I'm choosing as a running index not j or k or so, is because mathematicians like to use I as the complex unit, and engineers like to use j, so it's already predefined. Of course, we could do the following nasty trick. We say by mistake during our computations, j was put to 5, and then we can reinstall it as the square root of -1. And if we run it again, then you would see it's reinstalled to the correct value. But if you just would use j or I as a running index, well, it would be left with the value of 5 at the end of the routine, and then you do some computation with complex numbers. And of course, the computer doesn't know that you were misusing this number, and that's why I always, by tradition and the recommendation to everybody working with me, I label these running indices with double symbols. So it would be natural for me to say from kk equal 1 to 5, or kj or jj or something like this, because then it looks like an index, like a running index, especially if you do it in a consistent way, and doesn't destroy one symbol letters like the dimension of a subspace or an imaginary unit. Okay, so clearly here you see what's going on. You're seeing that you're getting the binomial coefficients, and this is just what you expect. Now, instead of 11, of course, you can take another number. I see. Yeah, okay, here it's written in a decimal way, but if you're rewriting it now just for one term, you see that you're getting again a polynomial now of higher degree. And I would say now let's do it a little bit more in this way. So I'm rerunning this coefficient. Here, nothing has happened because the leading terms are still the same, except that at the end, you would see it's stopping with 0, 0. Okay, now this is should be for you the entry door to elementary probability. So I'm not spending much time on this here, but for me, the polynomial, maybe I'm writing here now 1/6. So this coefficient, and I'm redoing it. Then I would say the BB is a polynomial. Constant 1 is not appearing, and then you have x to the first power, second, third, up to the 6th power. So you have a polynomial of degree 6, and the coefficients which correspond to the monomial correspond to the probability of getting a particular number. So everybody knows, if you ask what is the probability of getting a 3 with your fair dice, then it's 1/6. Now, the interesting thing is that you can ask, what happens if you want to know the probability of getting another number? Now, because we are doing things in this order of Matlab, we have to ask, well, if you multiply the polynomial by itself, there is just one term which is giving you x to the 12th power. So it's exactly the probability of getting 2 times 6, and that's exactly 1/36. If you check, you will find out this is 1/36. So it's just the same numbers that we had before, but everything multiplied with 36. So maybe I'm just to reinstall it. These are the real numbers, but if you take it in terms of units of 36, you will see it's just 1, 2, 3, 4, and so on. So what do you see exactly in position number 8? In position number 8, if you count it from no, sorry, that's something is, I see that there must be something missing. Yeah, here, yeah. So once more, I have to, we look from the end. So everybody knows if you have 2 dices and you look at the sum of the 2 independent dices, you will never get a 0, you will never get a 1, but you will get a probability with 1/36, 2 1s. That the poor guy who is getting 2 1s, the least value is of course symmetric to getting 2 6 for the lucky guy. How do you get, I don't know, let's go a little bit here. How do you get, this was 2 3 4. How likely is it to get 4? Or equally, how likely is it to get, this was 12, 11, 10. Turns out to be equally likely. So let's talk about 4. Well, we all know that you get 4 if you get 1 and 3, or 2 plus 2, or 3 plus 1. So the 2 ways. And here you would get, well, 6 plus 4, or 4 plus 6, or 5 plus 5. And so in this way, you are having an entry point why convolution is interesting for, in this case, integer valued probability, elementary probability, or you can say the dice is a random variable and the distribution function is coded in the polynomial. Later we will see it's a sum of Dirac measures or so, but I think this is a very important starting point. So why is the Fourier transform coming up so much through characteristic functions in probability theory? How can you understand discrete convolution? So that's exactly what I wanted to do here. I think that this is more or less the part that I wanted to discuss about this first thing, and then I'm switching now a little bit more in the direction of the Fourier transform already. So the first thing is, again, how do I get unit roots of order 8? Well, I wanted to present them later as a closed circle, so I'm making really a linear spacing where the first and the last will be identified from 0 to 2 pi and with 9 equidistant points. Now, what is the complex exponential function? So from real t goes to e to the it. Think of a long rope that you wrap up on the unit circle or a cylinder of diameter of a radius 1. And then you will see after a length of 2 pi, you will be back at the original one. Or if you write it in real and imaginary coordinates, think of Euler. You have cosine plus I sine or so. And therefore, we are getting a sequence of complex numbers. So these lines show you essentially, here I have the unit roots of order 9, but closed so that the first and the last value coincide. They are going, of course, in the mathematical positive way. So I'm using it U8 for unit roots of order 8. You could say, yeah, maybe we can compare also U8C, the primitive unit root of order 8 is the second one, and it should be the same. Okay, well, I have to be careful because the problem is radians and so on, but with the right formula for sine and cosine, I try to avoid an error message. It should be more or less cosine 45 degrees plus I times sine 45 degrees, but I think Matlab is working radii, so it probably would cause an error problem. Now, if you plot it, Matlab thinks it should plot in a nice way on my screen. But this is not the nice way for a circle. It will become an ellipse, therefore x is square, but I don't want to see the boundaries, so I take the axis off. And then on top of these things where I'm plotting in red stars, I would like to have this, and maybe I'm even repeating my red stars so that you see them a little bit better. I hope I have not destroyed anything. So what you can learn from this here, yeah. The plot routine, whenever it is given a complex sequence, it plots in the plane. The ordinary plot command, if you don't choose a color, probably it plots in blue. If you plot in green, well, it makes the line, and therefore it was important to have this last value included. But the red stars, and there are some symbols that you can use. You can use a blue plus or so. Then it would use a different symbol and a different color. And you would see this, well, yeah, it's not very nicely visible because it's already. Now there's another command that is self-made, which just puts the number of the coordinate, so the label, alongside with the position of this. So this is just the ordinary plot, but with numbers. And here you see the number 1 is overwritten by number 9. So for practical reasons, we will use only the 8 unit roots of order 8, of course. But here it's 1, and it shows you we are going with this command in the positive mathematical direction. I want to show you only quickly another command, and that's a command called stem_sil. So the stem command, yeah, maybe I should show you the stem command. That's a different command. Stem, that's kind of random 112. So this is a row vector of length 12, displayed not in a graphical way, I mean as a piecewise linear connection, but as a collection of needles. So the random values at coordinates number 1, 2, 3 up to 12 were these values. Now that's why we call this command stem_sil. It's a fancy command. It took a while to create it. It's essentially saying, well, if you have a function and it's supposed to be a periodic function, and in Fourier analysis we have a lot of periodic functions, then you would like to view it as a function on the cylinder, because there, and in the full version, you can rotate it and you can look at it from different sides. It tells you a lot about periodic functions because you see they don't have a beginning, they don't have an end. But so I wanted to just show the so-called Henning window. And there is a Henning with double N and a Hamming window with M, like Martha. They're slightly different. So this is, and I was really surprised. I learned from using such a plot what the Hamming window is. It's nothing else but cutting the cylinder with a plane such that at the lower point, which you cannot see here fully, it's not working here. It's touching zero. So, but it's used to create a function, and this function, now here I'm doing the same thing. I do a plot. Now the plot of a vector of length 72 is put on a range of 0 to 80. So in order to make it tight, so it's touching the last coordinate here, with ending really with 72, and make axis tight. I want to have a grid so that I can read off the value, what is roughly speaking the maximal value. Actually, it's 1 here. I can put a grid, or I can do the grid command once more, that is disappearing. And then if I have different windows open, I would like to come back to this original display. That's the figure with number 1, 2, 3, or get the current figure. So that's the last figure which has been opened. So of course it's this. So I have a short command. Sometimes I call it show graphics, SHG, but it's just instead of typing this command here. Now, something that's very important or useful to know with respect to polynomials is the use of the Vandermonde-matrix. So the first thing is, I see I have not done some command which was in a different window, so maybe I recreate this very quickly. So I'm opening up a new section. Yeah, and here I'm saying, well, we can evaluate polynomials at any set of points, and we can take random complex vectors of size 7. So this creates a random complex valued sequence of length 7, and set would be a sequence where this of complex numbers as well. It could be real if you want. The same convention, 7, 1. And then the question is, what is the Vandermonde-matrix? The Vandermonde-matrix is an important thing. You should look it up, but it's essentially the matrix that maps the coefficients to the values. So it's a bit unusual. Normally you're saying, I have a fixed polynomial, and I look at this at one value, at several values. We have seen the Polyval command is Polyval of polynomial with the coefficients, random coefficients at random points is of course a sequence of 7 values coming in the order of set 1, set 2, and so on. But my claim is that the Vandermonde-matrix is only depending on set, so on the geometry of my points in the complex plane, and you just have to apply it to the points. And now let's see if it works. Yeah, so great. So the Vandermonde-matrix works in this way. Now let me do, and that was the reason why I was telling you before this, the Polyval of A and Z, and Vander of Z with A. So you see this works fine, but if I would do this now, put it into a column mode. So we just change it. We have another, now it's a column vector. Yeah, that's something you have. That's interesting, yeah. Yeah, I see, yeah. So here it tells you everything is fine, because this routine converts both vectors to the standard format and compares it here. Whereas here, you have this effect of the difference between a row vector and a column vector is a matrix, and it computes the norm of a matrix without telling you, so to say. And that's why I leave this here. So the point is, the Vandermonde-matrix is telling you this. Yeah, maybe we do the following. I want to show you that you can, of course, recover the matrix, the coefficients from the values. So if I'm doing matrix multiplication with the matrix, of course, the inverse matrix will undo what the matrix is doing. So inverse of this multiplied to polyval of a polynomial A with Z. Yeah. Okay, so we have here some problem. Not sure what's happening. Yeah, probably it's not possible. I'm not sure about the format now. Yeah, okay, now it works. Yeah, you see, because I have changed the values of Z from column vectors to row vectors, I was inserting a column vector of points. Now the Polyval routine tries to preserve the format and to get the row vector of vector values, and of course a matrix multiplication with the 7 by 7 inverse Vandermonde-matrix only is possible if I have a column vector, and therefore I have to do it as a transposition. I don't want to conjugate it, but clearly the inverse of the Vandermonde-matrix is doing this. Okay, now it's another interesting thing if you take the Vandermonde-matrix and you try to say, well, how would I come back from the values of a, let's say, cubic polynomials, which has, of course, 4 unknown coefficients, to the coefficients, and then you would say, well, I probably should take the Lagrange interpolation polynomials. So let's assume your values are, to make it easy, -1, 0, +1, and 2. Then you build the Vandermonde-matrix, and you would find that the inverse Vandermonde-matrix has row vectors or column, I don't remember anymore, which are exactly the coefficients of the Lagrange interpolation problem. So undoing the evaluation mapping, coming back to the coefficients, has in this game a lot to do with the inverse Vandermonde-matrix, and in the approximation theory with determining the Lagrange interpolation polynomials, and they are the same. Now, the point that I would like to make, or where I would like to come here, is the discrete Fourier transform is really more or less the change from a sequence of coefficients to the values of a polynomial with these given coefficients at the unit roots of order n. So I was taking here in an explicit form the unit roots of order 5, just in order to make things not too big. And so you're seeing I'm going in steps of 1/5 from 0 to 4/5, leaving out the limit 1. And I take the exponential function, but this is with 2 pi I. So that's why the 2 pi appears so often. And then I'm doing the Vandermonde-matrix. Now, you can look at this, you would see that the Vandermonde-matrix has a constant 1 in the first row, and in this case in the last column. Why in the last column? Because the Vandermonde-matrix has x to the power 0 in the last column at all the points, so that's always 1, 1, 1. The second last column would be these values to the power +1, which would be exactly the sequence of unit roots of order n. And then you have the squares and the third powers and the fourth powers here. So if you would check, these are the fourth powers of the unit roots of order 5 but because 5 is a prime number, you will find out that these are again in a perturbed or permuted order, the unit roots of order 5. So there's not a big change. Okay, so if I rerun this section, we should see here at the end. Something is not working. Yeah, here my bar is a little bit disturbing. I hope you see it, that this is exactly the same. Now, I have to finish a little bit earlier today, but I would like to give you the message that the Fourier transform is really just doing the evaluation of the Fourier matrix. That's the matrix describing the Fourier transform is just FFT of I of the number n. So at the moment you just say, well, if I apply the Fourier transform command to the unit matrix, I'm getting a Vandermonde-matrix. Later on, we will interpret this result as saying, well, the discrete Fourier transform is a linear mapping. If I realize the linear mapping by matrix multiplication, which is of course a very inefficient way, but a way to understand what's going on, I would get a matrix. And oh, this matrix is on the one hand up to some normalization factor, a unitary matrix. So the columns are nice orthonormal bases in the complex sense, and they are Vandermonde-matrix. And I would say this combination of facts is the best choice that you can have. Now, we have seen in this very little example that you can recover the matrix, the values of a polynomial with the correct number of distinct points. So I was choosing polynomials of degree 6, therefore 7 coefficients, and I was recovering from the inverse matrix. But we can also ask that maybe we can do it here. What is the condition number? Is this a good matrix? And then you will find that's probably not such a good matrix. I'm running this experiment once more. Yeah, it's 10 to the 4. I'm rerunning it with new numbers. It's 10 to the 3. I'm rerunning it just size 7, remember, it's not a huge collection of points. And you can do it now, of course, with larger numbers, and you will see that for random points, the recovery is not very stable. However, if you're choosing 7 points in the optimal way, and that means you're taking unit roots of order 7, you would find out that this condition number would be quite nice. So maybe we can put it here. Condition number of U5. I hope I didn't make any mistake. And I rerun this command. And you see it's 1. And that's already an indication that this is and must be a very nice matrix, actually a unitary matrix or so. Now, I think it's not meaningful to start anything new here. So the only thing that I would like to tell you is that the FFT is, of course, an implementation of the discrete Fourier transform. And I don't write the formula now, but what I would like to show you is very simple first-hand observations. What is the FFT of a random vector of size 4, of a row vector and of a column vector? And the answer is, of course, the answer is again a row vector, so it preserves the length and it preserves the shape. But in both cases, you're running, even if you start with the real valued functions, with you're going into the complex domain. Let's take another random complex vector of size 7 maybe, and then you're asking what is the norm of FFT of RD compared to the norm of RD. Okay, you will get some number. Now, you can say, well, is this number depending on my random vector? And you will see, of course, that the random vector is changing, whereas this quotient, oh yeah, sorry, yeah, I'm doing too many things. But of course, this number, yeah, the section is too long. Something is wrong here. Yeah, here, but this number is not changing anymore. So this is one thing, and of course you can ask. So I should put this separation sign here, so you can guess what this is, and it will be the square root of the length of 5 in this case. If I rerun it, you will see that this number, yeah, of course, the length of the vector is 7, and that should be the right number now. So now everything is fine. And the other thing is, if you're saying FFT of I of 7. So Matlab says, oh, I'm applying the matrix, the FFT command not to a matrix. It doesn't know that the FFT2 exists, but to a collection of vectors. And then I want to know whether multiplying my random vector, sorry, I should do now a column vector. I need a column vector. And I'm finishing. So if this is I of 7, and then I want to know, is it the same as applying this matrix to the vector, or to do the FFT of that vector? And to take the difference of these two things, that should be fine. And you see this is the same. So the point is, this matrix F, and that may be the take-home message for now, is a Vandermonde-matrix, and that gives you a lot of good properties, and especially if these unit roots are numbers like a power of 2 or a natural number with a lot of divisors. And this side tells you can do it very fast and very quickly, and you can recover a return. Yeah, last thing is maybe what is, if I compare the norm of the inverse of F with the F transpose conjugate, but it's symmetric anyway, therefore I can say I want to compare it with the transpose only. And you see the difference is just numerical precision, but there is a factor here, and the factor turns out to be just 1 over n, so it's 1 over 7. The inverse matrix is therefore, and maybe I'm just doing this now, I divide by 7, so I divide by 7, and then you see that the inverse is just the conjugate, and that's why the inverse Fourier transform is just having a minus upon a plus as compared to the forward Fourier transform, which is a minus e to the 2 pi I all the time. Okay, I think I just finish now the recording, and I thank you very much.